All right, chapter 12, all about calculus. So, learning goals for today. Calculate the plot derivative using a limit. Calculate the plot integral using the reverse power rule. So, we're going to do this one the hard way and the easy way. This one only the easy way. I'll show you what I mean in just a second. There are some Common Core standards associated with this, which I'm sure you're very interested in. So, Newton's paradox. Calculus was born in the mind of Sir Isaac Newton one day when he was occasioned by the fall of an apple. We've talked a little bit about physics and stuff in here. So one day, Newton's walking around outside. He's kind of a weird dude, sort of a recluse, so he didn't get outside much. So it was somewhat fortuitous that this occurred. So he's walking around outside, and he was occasioned by the fall of an apple. It's probably apocryphal, in other words, made up, that it hit him in the head. It probably just fell on the ground. And it was one of those days where the moon was in the daytime sky, visible. So he looked at the apple, looked at the moon, and realized the same force was acting on both objects, gravity. So he tried to describe and quantify gravity, and the mathematics for it just simply didn't exist. Because he thought about, if you think about how gravitation works. So if I had the speed of an object affected by gravity, so a falling object, with relation to the time it has been falling, it's not going to be a straight line. You see, it's going to be a curve like this. So the rate of change has a rate of change. You see what I mean? It's like an acceleration vector. So in your car, if you hold the gas steady, you can stay at 40 miles an hour. But if you floor it, suddenly you have an acceleration vector. So the rate of change is changing. And that's what's happening when gravitation affects an object. And so he thought about, how can I describe this? And he considered the slope formula, which we'll talk about in just a minute, the difference quotient. But he figured out a way to find this exactly. And it was using the first mechanism, which is a limit. And the limit allows you to simulate division by zero. So we still can't actually divide by zero, but we can pretend to divide by zero, if you will, using the mathematical mechanism called the limit. So, and the only thing we're going to do, the only mechanism we're going to use to evaluate a limit is to algebraically remove division by zero and then plug the value in, or use a graphical analysis. So we're either going to graphically analyze it and see what the limit comes to, or we're going to plug in the value. So when I say that, so if I look at and this actually isn't the best example in the world. Let's do yeah, I like that one better. So if I have a curve and I have a hole in that curve, in other words, a spot of discontinuity like this, where the function approaches the same value from the right and the left, but there's that empty spot where division by zero occurs, then the limit exists. If I have an infinite type discontinuity, you remember that's where it goes to positive or negative, or both infinity around the discontinuity, then no limit exists. If I have what's called a jump type discontinuity, and you'll remember that those only occur in the exotic piecewise type functions that we don't often see, then it also doesn't have a limit. It has to be like this. In other words, approach the same value for both sides. Provided that's the case, the limit exists. So let's graphically analyze this and see if we can determine what that limit would be. So if I look at this graph, 3x squared minus 9x divided by x minus 3. So, and I need a little bit more y value. So let me just zoom 6, I should do it. So I'm concerned about its behavior at 3. If I hit trace and 3, you'll see the y value does not exist. You remember when I did this back in chapter 1, and I zoomed in and zoomed in and zoomed in until there was a little tiny spot missing? So that's exactly what would happen here. If I zoomed in and zoomed in, there's a little tiny pixel missing. So the value 3 is undefined because it creates division by zero. But the limit as x approaches 3 does exist, because you see it has this behavior. It's coming to the same value from both sides. So if I put in a value very close to 3, but not quite 3, like 2.99, I see that's 8.97. 2.99999. See, I can get arbitrarily close. I'm not touching you. I'm not touching you. Can get as close as I like. And I get closer and closer to 9. If I come on the other side, a little more than 3, see, I'm still getting closer and closer to 9 from the other side. So it is approaching 9 as a limit. And as a consequence, we say the limit as x goes to 3 of f of x equals 9, even though the function is undefined at 3. The limit gives us information we would not otherwise have. So that's a graphical analysis of a limit. Okay, any questions about that? We already had quite a bit of limits, but it was very early in the book. And it's one thing about this book I don't really love is the fact that they introduce limits very early and then never again until this chapter. But can't be perfect, I suppose. So let's find a couple limits here. First of all, if we have this function 2x cubed, and my 3 looks a little wonky there, let me fix it. So 2x cubed minus 8x over x squared minus 4. And we want to find f of negative 2, so that's 2 times negative 2 cubed minus 8 times negative 2 over negative 2 squared minus 4. So that's going to be 2 times negative 8, or negative 16, plus 16. Negative times negative is positive, over 4 minus 4. So I get 0 over 0, which is an undefined result. It does not matter what the numerator is. If the denominator is 0, this is an undefined result. So the numerator is effectively irrelevant when you have a 0 denominator. It's always undefined. So this gives us no information. However, the limit as x approaches negative 2 will, and we can use our graphical analysis technique. So if I replace this function with this one, which is 2x cubed minus 8x divided by x squared minus 4. Looks for all the world like a continuous function, doesn't it? But if I trace at 2, see that it doesn't actually exist there. As we have found algebraically, it's an undefined point. But if I get real close, like 1.99999, it's at 3.9998. And if I go just past 2, 2.00001, I'm really close to 4. So the limit here is 4 by graphical analysis. It must approach the same point from both sides for the limit to exist. And again, the only time it would not is if you had an infinite or a jump type discontinuity. Jump types are exceedingly rare. So most of the time, if you have a discontinuity, it's going to be a consequence of division by 0. And it's going to be, the limit will exist. Okay. All right, here's one for you guys. Tell me what the g of 3 is and what the limit as x approaches 3 of g of x is. You know, get mixed up or something. Right. Caden, what's G of 3? Indeed. Division by 0. What's the limit as x goes to 3 of G of x, Abby? 3. Questions about that? All right, limit, sir.
Can you do the limit?
Sure. So again, we're just doing it via graphical analysis, and when you guys actually do go to Calculus 1, there's a lot of mechanisms to calculate limits, a lot of algebraic mechanisms. In fact, you're going to be sick of them. There's so many. So I'm teaching you one and only one way to do it, which is graphical analysis in this case. So all we're doing is looking at the graph. Make sure you get your parentheses in there right, or you're going to get a bad graph. And then we're looking at its value very, very close to 3, both from the right and the left. See, we're really close to 6 here. If we go on the other side of it, really close to 6. So it's clearly approaching 6. And that's a very, I don't know, brute force mechanism for finding the limit. It's not nearly as elegant as the algebraic mechanisms you'll be taught later, but it works. And it's pretty good for folks that are just introduced to the concept. Okay, so derivatives. This is where Newton found how to find the slope of a curve. So the slope of a curve. So if f of x is the function, this is just how you write it. D over d of x of f of x means to find its derivative, which is often written as f prime of x, which is the rate of change in that function for all x values. So it'll be an expression of x if it's a curve. So we'll have to plug x in, and then it'll give us what the slope is at any given point x. So it models nonlinear rates of change that have an acceleration vector. Like instead of just holding the gas steady, you've now floored it or stomped on the brake. Either of those apply an acceleration vector. Positive in the case of the gas, negative in the case of the brake. All right, so this is the notation for the derivative. How do you find it? Well, there's a couple ways, hard way and easy way. I'm going to teach you both real quick. First of all, the hard way, and this is important because it helps you understand Newton's thinking. So Newton thought about, if I want to model the rate of change on a curve, I can pick any point x and any other point that's a little bit ahead of it. We'll call it x plus h. And so the resulting value on the y-axis is going to be f of x and f of x plus h. So these 2 points are going to be x comma f of x and then x plus h comma f of x plus h. So those are 2 points on the curve that are some arbitrary distance apart, h, whatever we want it to be. We can make it smaller and smaller and smaller and smaller. The smaller it is, the more accurately it will represent the slope of that function. But if we make it infinitesimal using the limit, in other words, if we take the limit as h goes to 0, suddenly we have the actual slope. So let me show you how to do that. You're going to use the good old slope formula. Remember rise over run? Would you have imagined it would manifest here this late date? Maybe your first introduction to a complex formula. And here it is, recurring. Rise over run. So we're going to say the slope So if this is f of x, then f prime of x is going to be the limit as h goes to 0 of y2 minus y1 over x2 minus x1. Slope formula, also called the difference quotient. So if you ever see on the ACT or the statewide dual credit test, and sometimes you will have one or two that mention what's called the difference quotient. This is what they mean. This application of the slope formula to 2 points that are an arbitrary distance apart. We can simplify this a little bit. By canceling out the x's in the denominator. Now, the simplest way to evaluate a limit is to just plug the value in. You can't do it because it creates division by 0. But sometimes you can algebraically eliminate the h in the denominator. And if you do that, well, then you can just plug in h equals 0 and find the derivative. But this is the formula for the derivative of a function, the brute force formula, the difference quotient. So again, we're taking h and making it an infinitesimal sliver, the smallest little thing you could imagine. So let's do some of these. First of all, f of x equals x squared. So I say, I want to take f prime of x, I want to take the limit as h goes to 0 of f of x plus h minus f of x over h. So that's the limit as h goes to 0 of x plus h squared. I'm sorry, minus x squared over h. So continuing to simplify, that is x squared plus 2xh plus h squared minus x squared over h. Don't lose your limit. That limit still needs to be hanging out there to the left. So the limit, until we plug it in, then we can get rid of it. So x squared and minus x squared cancel out. And I'm left with 2xh plus h squared over h. Now I can factor an h out of that numerator. And cancel those two out. And now do you see I can plug in h equals 0, evaluate the limit, and it's actually 2x. Yeah. So I factored out the h, so 2x plus h. Plug in the 0, I get just 2x. So the slope of x squared, that parabola that you know the graph of so well, because you graphed it 1,000 times by this point in your math career, at any point, its slope is exactly 2 times the input. So if I pick 2 on the parabola, its slope is 4. If I pick -5, its slope is -10. So I now know exactly and intimately its slope at any point on that function. A very powerful tool is the derivative. And then for this next one, it's very similar, but probably worth doing twice just because it's so complicated. So we'll do one more of these. So we're going to take the limit as h goes to 0 of f of x plus h minus f of x over h. Plug those in for that function. So I get 2 times x plus h squared minus 2 x squared over h. Don't lose your limit again. I had to do that. It's been a while since I've done calculus. So don't get rid of that limit until you plug in h equals 0. Continuing on here, I've got 2 times x squared plus 2xh plus h squared minus 2x squared over h, and we're still taking the limit as h goes to 0. Okay, so distribute that 2 plus 2xh plus 4xh plus 2h squared minus 2x squared. So once again, we've got something that cancels here fortuitously. And I can factor an h out of that, those remaining terms in the numerator. So I get the limit as h goes to 0 of h times 4x plus h over h. If I cancel those out, plug in 0, get 4x. So 4x is the slope of that function at any point. So 2 times x squared, if I plug in 6, the slope is 24. If I plug in -8, the slope is -32. Or exactly for every point on the graph now. And I did another one down here. These are kind of tedious notation-wise. You guys have any questions about that? So now the easy way. And you're going to be like, oh man, why didn't you just show us that first? Because it's so much easier. So the power rule for derivatives. Anytime I want to derive something, a polynomial term, I can use this shortcut. So if I take the previous example, remember I did 2x squared. So in this case, the coefficient is 2, so that's the a here. The variable is x, and the exponent is 2. So I just do n, which is 2, this exponent, times a, which is also 2, times x to the n minus 1, or 4x. So you see how quickly that solved that previous problem. We spent so long. This is the shortcut, the power rule for derivatives. And I'll do a couple. I've got another example up there. But we'll, oh, and also, constant terms derive to 0. So if I take, if I have like 1 here, that just derives to 0. And it makes sense if you think about it, because think about how the graph of a constant looks. See how it's just a horizontal line? Well, what is its slope? What's the slope of a horizontal line? 0. So it derives to 0. So any constant term derives to 0. Important mental note to make. You'll fumble around with those trying to apply the power rule. It won't make a lot of sense to you. Okay, so let's do a couple examples of these. And polynomial terms can be derived each one at a time. And whatever sign they have persists. Okay, so first of all, this term, so that's 3 times x to the 3 minus 1. Old exponent times the coefficient times the variable, which is x, to that original exponent minus 1. A little pattern. You'll have to do it a few times, but once it clicks, it'll click. So this is 2 times 12 times x to the 2 minus 1. Another trick, because the power rule is going to be a bit confusing for linear terms as well as constants. For linear terms, in other words, if x is to the first power, they derive to the coefficient. So whatever the coefficient is, in this case 1. And remember that constant terms derive to 0. So linear terms derive to just the coefficient value, and constant terms derive to 0. So simplifying this, some TI calculators can do a few things in calculus. Wolfram is a more reliable source. So anytime you want to check your work, Wolfram's probably where you want to go. And if you put in d over d of x, that means the derivative. And if we do 3x cubed minus 12x squared plus x plus 3 with respect to x, it'll give us the answer. So 9x squared minus 24x plus 1. And I guess that last comma x wasn't necessary, but so you can use Wolfram to kind of confirm your answer. Don't use it to do the work for you. That's laziness. But using it to check your answer, definitely a good strategy. All right, B is a little more challenging here. So in this case, notice I've got a fractional exponent. So he comes out here, and I'm going to move this negative sign outside the term. Only put the negative sign once. Don't put it in two places or it'll be a sign error. So negative 1/5 times 7 times t to the 1/5 minus 1 power. And then this is a constant term, so it derives to 0. So that's negative 7 over 5t to the negative 4 over 5 power as my derivative. Okay, so a couple for you guys. Tell me what the P prime of S and Q prime of X are. Using the power rule shortcut. Cal 1 teacher's going to be so impressed. She guys already know. Assuming you can retain it. Everything else is right. Gotta get to know yourself. You don't run around. Okay. So let's talk about these. Whitney, what about P prime of S?
Negative 12s plus 2.
Excellent. So anywhere on this slope or on this function, if I plug in an s to this p prime of s, I will know the function's slope, its rate of change. So p prime of s tells us the rate of change of p of s at any s. What about q prime of x, Blake? Okay, that's fine. Yeah, I did kind of go fast there. Hayden, what do you think? Good. Very good. Excellent. You guys see why that's the case? Now, this one requires some fractional arithmetic, which is the bane of a lot of high-level mathematicians, believe it or not. A lot of people that can mentally do the calculus can't mentally do the arithmetic, because those are not exactly as overlapping skill sets as people might imagine. For example, one of my best friends, Alex Campbell, is the greatest arithmetist I've ever seen. He can do like 42 times 17. Boom. He'll say it before you can even think it. But when it comes to calculus, he's not so great, as he'll admit. He squeaked by that class in college. But his arithmetic skills are out of this world. And often the inverse is true. Now, people can really master those calculus concepts, but they have to depend on a calculator for the arithmetic. So don't feel bad if you have to use a calculator for this kind of stuff. So the next great concept in calculus is the integral. So this is the brainchild of Leonhard Euler, who was the Einstein of his time, literally. His name was used to describe someone that was a genius in his during his life. So his name was used in the same way we use Einstein's name to describe a brilliant person. Euler, and he created what's called the integral. But a better way to describe it really is the antiderivative. So in an equation, you remember when you first started doing multi-step equations and you had to use inverse operations. So if I want to invert multiplication, what do I use? Division. Those are inverses. They undo each other. What about addition? Right. This is a tricky one. You learned this in chapter 3. What about the logarithm? Here's the answer. Starts with an E. Exponentiation is what I'm looking for. So that undoes the logarithm, and the logarithm undoes exponentiation. Roots undo powers, and so on. So for every mathematical entity, there's its opposite number. And for the derivative, the opposite is the integral. And the name antiderivative kind of drives that home more completely. So if you're going to memorize one of these two names, probably the second one would be. So the integral, or the antiderivative, is the area under the curve. How is that the opposite of the slope? Well, it's hard to describe. Just trust me, it is. So between any 2 points, if we have what's called a definite integral, we can find it using little tiny rectangles. So you see how that would model the slope? And the skinnier I made those rectangles, the more precisely it would measure the area under the curve. To the point where if I took the limit as the distance of those rectangles, we'll call it h, approaches 0, then it is exactly the area under the curve. We won't do this one using the limits. It goes beyond the scope of this class, but it can be done. Instead, we're going to use the shortcut from the beginning. But two important things to note. For indefinite integrals, these are integrals without bounds. Notice there's no a and b on top of the integral symbol. This is called an indefinite integral. The notation looks like this. For the definite integral, where you do have bounds, it looks like this. And this formula is the fundamental theorem of calculus. In other words, the most important idea in all of calculus. And it describes the behavior of the integral, the area under the curve, which is somehow the opposite of the slope. Sorry.
What's that little thing at the beginning?
That's the integration symbol. It's like a stretched out S. So there's no real specific name for it. Euler made it up because it's a sum of the area of triangles. He thought S kind of made sense, and so he created this stylized, funky S. So that is an invention of the mind of Euler. His name is spelled E-U-L-E-R, which looks like Euler, right? Don't say Euler. Calculus teacher's going to roast you so hard, your grandma's going to feel it. That is one way to tick off your calc professor, is to call Euler Euler. Because it's like mispronouncing the name of Elvis. It's one of the greatest minds to ever live. You didn't even say their name. He is a fairly obscure figure. I doubt you've ever heard of him outside this class. But to the mind of the great mathematicians, he's like Elvis, or some great figure in history that you would surely know. So Euler, not Euler. They'll be impressed, trust me. All right, so again, that second formula is called the fundamental theorem of calculus. And it says the integral from a to b of f of x with respect to x is the antiderivative of b minus the antiderivative of a. Remember the fundamental theorem of algebra, or at least its most important corollary, which is a polynomial of degree n has exactly n complex solutions. Or maybe you didn't remember that. But you should. Because I've mentioned it probably, I don't know, 6 or 8 times. Okay, so again, we're going to use only the shortcut method, which is called the reverse power rule. So it undoes what the derivative, what the power rule does. So we take this original term in a polynomial, add 1 to the exponent, divide by the new exponent. Now, if you have an indefinite integral, you have to add this c value, which is the unknown constant. Because you remember what a constant derives to. 0. So we don't know if it was there or not. So we add the unknown constant of integration to an indefinite integral to account for some constant that might or might not have been there. Because if it goes to 0 when I use an operation, how do I know if it was ever there or not when I go in the other direction? I don't. So that's the c value. Now, if you have a definite integral, one with bounds with an a and b value, I don't have to worry about this constant of integration. So this only applies when we're using indefinite integrals, ones without bounds all the time. Okay, so reverse power rule, let's apply it. Add 1 to the exponent, divide by the new exponent. So here I've got definite integral, so I don't have to worry about the unknown constant. It's definite because we have bounds, the top and the bottom, 3 to 7. Now we're going to integrate these terms. So add 1 to the exponent, divide by the new exponent. Now, do you remember how linear terms derive to just the coefficient? Well, in the same fashion, constants integrate to just that much times x. So minus 1 times x. Now I'm going to use this notation to indicate I have to evaluate it between 7 and 3. So remember, that second part of the fundamental theorem of calculus. Now we're going to plug in 7 here. And then minus. And I'm going to use a big old delineator so that I don't make a sign error. And I plug in 3 now. So 2 times. So that's the antiderivative evaluated at b minus the antiderivative evaluated at a. The area under the curve of this function from 3 to 7, or its antiderivative if you prefer. Figuring this out, 2 times 7 cubed. 7 cubed is 343, I believe. Let me double check myself. Oops, not 37 cubed. 343 is right. Times 2, 686. 2 times 3 cubed. 3 cubed is 27. 2 times that is 54. And then negative times negative is positive. I'll plug that in the calculator again, because there's a lot of room for error there. And then I'm going to hit math, enter, enter, to get 620 over 3. So that's my answer. Put it up there so it's not in the way. Let's use Wolfram to check our answer, shall we? So the integral from 3 to 7 of 2x squared minus 1. INT is the Wolfram command for integral. So 2x squared minus 1 from 3 to 7 with respect to x. Exactly right. So confirming our answer. The area under the curve, look at it. Isn't that interesting? Now let's do the indefinite integral, which is really easy by comparison. None of this calculation is necessary, but we do have to remember the unknown constant of integration. So I've already found the antiderivative here, so that's going to be the same for this one. Capital F of x is how we describe the antiderivative. Don't forget that unknown constant of integration. Now, in my notes, I had C sub 1, because it's often the case in differential equations, you'll have more than one constant of integration. You will not see that in Calc 1, nor in my class. So C is fine. The foreseeable future. There will come a point in the distant future when you must use more than one constant of integration, and its subscripts become necessary. Okay, so let me give you guys a couple of these. Tell me what the definite integral here is and the indefinite integral here. And the type of problem you see on part C can be done on some TI calculators. If you look under math and FNINT, if you have that function, it'll do it for you. But try to do it by hand before you use that to check. Let me know if you get stuck, confused, etc. Yes. Well, for every case, you're going to add 1 to the exponent and then divide by the new exponent. So x squared is going to become x cubed over 0.
Right. See, I got that.
Okay, so with this one, same process. So we add 1, so it becomes 2x squared over 2, which reduces to just x squared. And for the minus 12, or minus 1, the minus 1 becomes minus 8.
So what's your those two? You already just do them separately.
Separate.
Okay, I mean, thank you. You're welcome.
Uh-huh. Well, so for each of these terms, we're going to add 1 to the exponent. So instead of x squared, it's x cubed. Then we divide by that new value. So it's x cubed over 3. Then for the second one, it's going to be 2x squared over 2, which is the 2 and then for minus 1, so maybe use a constant. It just becomes that times x. So minus x. That's it. Yeah. Oh my gosh. I'm either the best teacher in the world, but you're a real smart kid. I'm utterly impressed. Maybe both. Minus. Remember f of b minus f of a. So that's what the minus. I'll do it. Excellent. I got these played. Be careful with the use of delineators though, because it's really easy to make a sign error. Spend about another 30 seconds or so here, maybe a little less. Everybody's finishing up. All right. Okay, Bryce, what's my solution to part C?
1225 over 3.
Excellent. Everybody see why that's the case? And then for the indefinite integral, what do you think, Elizabeth? So it's going to be the same as the expression you used here, but plus c. So x cubed over 3 plus 2x squared over 2, which is just x squared, and minus x. Can't forget that plus c. So the indefinite integral, the trick is to add that plus c at the end. We don't know if it was there or not. Okay, so now you have all the tools necessary to recreate one of the great math problems of history. So that, remember that real smart guy over there with the sleeping cap on or something? So he once thought about the relationship between differential equations. So if I can show that two functions are solutions to the same differential equation, which relates the slope to some other aspect of the function. So if I can show that two functions are both solutions to the same differential equation, I'm effectively showing that they have the same slope. And you see how if two functions have the same slope everywhere, they have to have the exact same shape like this? But they don't necessarily have to be the same function. However, if I can show that two functions both have the same slope and share at least one point, do you see how if they share at least one point here, they must share all points if it's the same shape? So he thought about two very interesting equations with respect to that relationship. So he thought about, what if f prime of x equaled I times f of x? So the derivative, the first derivative is the imaginary unit times the original function. So that's a differential equation. It relates the derivative to some expression involving the original function. And he thought about two functions. He thought about his Euler's equation, which is cosine theta plus I sine theta, and then this exponential equation, e to the I theta power. So he thought about those two functions And he said, if I can show that they're both solutions to this, then I would show they had the same slope everywhere. He had some sort of intuitive sense that they were the same, but he couldn't quite prove it with any other mechanism than integral calculus. So if I find the derivative here, now the derivative of trigonometric functions is just like a chart, okay? So like cosine derives to negative sine. Sine derives the cosine. So the rate of change for the cosine is the negative sine. The rate of change for the sine is the cosine. Why is it? Well, not really sure. If you figure that out, there's probably some kind of big mathematical prize awaiting you. But just trust me that it is. So if I did I times z, in other words, if I multiplied this times I, and remember that I squared is -1, boys and girls. Or people say minus. Do you see how these are the same? These are the same thing. So z prime equals I times z, making it a solution to that original differential equation. If you can't follow this, that's okay. It's one of the great proofs of math history. But if you can, that's awesome. So z prime equals I times z. Now, with respect to e to the x, or in this case, e to the I theta, it has a really unique behavior. Perhaps its most important aspect is e to the x is its own derivative. In other words, the function's value is also its rate of change everywhere. So the derivative of e to the x is e to the x. It is its own derivative. It's the identity of the derivative function. Do you see what I mean? Like 1 is the identity for multiplication. 1 times 1 is 1. Well, the derivative of e to the x is e to the x. It's fascinating. But there's something called the chain rule, which says if we have a function in a function, see how its exponent is two values multiplied together. So that's kind of a function within a function. So we use this thing called the chain rule to get this result. So once again, I can see that the derivative is equal to I times the original function. And once again, we have a solution to this differential equation. So we've shown that Euler's function and this function have the same slope everywhere. One more thing, if we can show that they share one point, one and only 1 point, it must be the case that they're the same function. In other words, we can set them equal. So if I plug in 0 for each of these, first of all, for this one, z equals cosine theta plus I sine theta. So if I take z of 0, not theta, 0. Then cosine of 0 is 1. Sine of 0 is 0, remember from the unit circle. So this term goes away. So that function, if I plug in 0, I get 1. What if I plug in 0 to that second function? Y equals e to the I theta. So if I plug in 0, I times 0 is 0. Anything to the 0 power, ladies and gentlemen, is 1. So I've shown they have the same slope everywhere, and they are indeed, they share at least 1 point, so they are indeed the same function. Those two functions are equal, meaning we can set them equal like this. Now, if I plug in theta equals pi, I get one of the most interesting results. This is the special case of Euler's formula. If I plug in theta equals pi, I get one of the weirdest results in all of math history. And long, long ago, way back in chapter 1, I teased this and told you I'd show it at the end. I'm sure you guys have been waiting with bated breath. Well, here it is. So remember that cosine of pi is -1, sine of pi is 0. So this is, or more commonly written as, Euler's God function. In his mind, proof of a higher power. Euler was once challenged by Catherine the Great, who was the ruler of Russia, great emperor, biggest in the world, at least geographically, to debate in front of her court the existence of God. And he was to debate Diderot, a French philosopher and atheist. So Euler was kind of a prima donna and not a really nice person. But he showed up, surprisingly. But instead of following the rules, you know, there was supposed to be this person presents a case, this person presents a case, then this person rebuts, then that person rebuts. So they were going to have an organized debate in this way. Instead, Euler dashed in, wrote an equation on the board that was intended to stand in for this, said, "Thus God exists," and walked out. Catherine the Great was impressed and decided to award him the victory. So, in Euler's mind, this is proof of a higher power. And I don't pretend to understand it as well as Euler did. That would be foolish. However, it does present a pretty compelling argument. Because think about it like this. At least there's some grander structure to the universe that we can't fully explain. The reason why is E comes from the exponential. Exponential growth, like what's evidenced in bacteria in nature, or the way radioactive matter decays, is a logarithmic equation, which is a relative of exponentiation. Pi is from the world of geometry. Circles, squares, shapes, imaginary two-dimensional figures. I is from the world of polynomials, imaginary solutions to polynomials that have no real solutions sometimes. And then 1 is the fundamental unit of the real number system. So it's akin to this. Imagine if I went up on top of a mountain and I found this funky artifact. I went down into the bottom of the ocean and I found another funky artifact, and I noticed it kind of looked like the first one. Then I went into the desert and found a third, and I went off to some other location, like North Pole or something, found a fourth one. And then they all fit together perfectly. What would that mean? Well, the conclusion I come to is somebody created that. Something made that pattern. It could be some sort of universal mechanism, who knows what. But to Euler's mind, it was evidence of a higher power. Pretty interesting nonetheless, if you agree with him or not. All right, ladies and gentlemen, that is calculus. And also, that's pre-calculus. We're done. Congratulations. Let me open up the very last quiz for you.